Okay, welcome to the Monday seminars. I am Chris Marone. I am delighted that we can start again this fall. We've been going for quite a while. I'm sure there are some new people. Welcome, all of you. If you've been here before, then you know our normal style. And if you haven't, let me just say that this tends to be quite informal, despite the fact that we have fabulous high-class speakers like Professor Curtis, who's going to talk to us today. The mode has been always quite informal in the sense that if you'd like to start joining these early, we have sort of 5 or 10 minutes at the beginning of just chatting and saying hello to people, meeting people. So please join. And during the talks, and I've already checked this out with Andrew, it's okay. Typically, we ask people to yourself at the beginning, and then during the talk, if you have a point of clarification, just go ahead and unmute and blurt your question out. You could put things in the chat, but I think Andrew doesn't mind being interrupted by small points of clarification. At the end of the talk, we will have up to 30 minutes or so of an extended question and answer and discussion session. So there typically is plenty of time to have a real discussion and some questions. And I think it's kind of one of the nice things about an online seminar, because we don't mind going for a little bit of time. The people who have to leave, of course, will leave, and everyone else can stay and participate in the discussion. So without anything further, I will ask you to mute yourself and to join me in thanking Andrew Curtis for putting this talk together. Andrew, go ahead.
Great. Thank you very much, Chris. So, yeah, so I'm a professor in Edinburgh in Scotland. And actually, while it's me giving this talk, I'd just very much like to mention the 3 people in bold just beneath my name there. So Atif Nawaz, Xin Zhang, and Shubin Zhao. And they've all been PhDs and then postdocs in the group here in Edinburgh. And what you're going to see today, all of the results have been parts of work that we've all done together on their PhDs and postdocs and so on. And also, we've had plenty of input along the way from some of our industrial collaborators, so Paul Williamson, Angus Lummis, and Rodney Johnson in particular. So thanks very much go to them, and lots of acknowledgement for what you're about to see. So I'm going to talk today about Bayesian inference for seismic imaging and interrogation problems. And my goal in this talk is going to be to describe the family of subsurface Earth models that are consistent with some measured data that we have. So when I say the family, I want to find all of the different models, and in some sense characterize them or describe the family of all the models that are consistent with the measured data, because if they're all consistent with the data that we have, then that means the data cannot discriminate between any of those models. In other words, that family is what we mean when we use the word uncertainty. So this is the aim of this talk, is to describe the uncertainty in imaging and inverse problems and interrogation problems of the Earth. But that sentence at the top is really the definition of what I mean by uncertainty. Now I'm going to focus on imaging problems here. So I'll be talking about all the way through, we'll be dealing with synthetic problems where we know the true model, because what I would like to focus on are the advances in the methods and algorithms that have taken place in the last 4 or 5 years that start to make this possible, to this goal possible to achieve in the real Earth, in the 3D Earth. So the models will be models such as the one you're seeing in front of you, where the colors might be seismic velocity or density. And the types of data that we're talking about are what we record on a set of receivers. So, for example, the triangles here. If we inject some energy in from some source on the surface, the energy propagates into the Earth, it interacts with the subsurface, reflects, refracts, diffracts, comes back to the surface. And whatever we record, that will be our data. And those will be what we call the seismic waveforms. And the models that we're dealing with will be all acoustic in this case. So the velocities, the colors will represent acoustic speeds of, or wave speeds of acoustic waves. Now, The reason that I want to know the uncertainty structure of these types of models, given some data, is that it can be that, for example, structures like this little green patch here might represent a putative reservoir where we want to store CO2, extract geothermal energy, something like that. And so we would probably like to use this data to characterize that structure and answer specific questions about it. So, for example, how large is that potential storage reservoir there in green? Now, if we have a family of different subsurface models that are consistent with the data, then all of those models are going to look a bit different from each other, and have different structures visible here. And so the size of that structure, the putative reservoir, is going to change. And so we're going to get not just one estimate of that size, but a range of estimates. And so what you're seeing here are histograms, 2 histograms of different estimates of reservoir size. And I've just normalized that into normalized units of pixels, actually, in this model. And you can see 2 different histograms, because on the left one, we've used seismic waveforms focused around 4 Hertz, so very low frequency. And we see that we get a very broad distribution of estimates of reservoir size. Whereas if we increase the frequency to 10 Hertz, we see that we get a far tighter hold on that distribution. And what the reason that we want this distribution is that it's giving us an upside and a downside to the reservoir size, and that's going to help us make risk-based decisions about whether to develop that reservoir or not, or how to develop it, etc. And so the idea of answering specific questions is essentially to set up an interrogation problem, what we call an interrogation problem, which is to interrogate the Earth using, in this case, geophysical data, to answer specific questions. And that's our aim. Now, what I would like to do is to be able to implement this and carry it out practically in the real world, so that means in 3D. And that's been a major challenge. But in addition, we don't just want to image the structures and calculate the uncertainty, we want to be able to monitor changes in those structures as we inject CO2, for example. That means we want to do it in 4D, where the extra dimension is time, so time snapshots of the Earth in different times. And anyone who's worked on imaging the subsurface using seismic data will know that the biggest step is actually finding the velocity models. And that's what we're going to focus on today. Acquiring the data and pre-processing the data, migrating the data, and so on to construct images. All of these steps are, I mean, they can be major steps, but as far as evaluating the uncertainty is concerned, they're all tractable. We know roughly how to propagate uncertainties through those types of steps. But finding the velocities is a different kettle of fish altogether, because the main advances in imaging over the last 20 years or so have been due to a method called full waveform inversion, which is extremely computationally intensive, and propagating uncertainty through that in 3D and 4D has until now been really out of reach. And so what I want to talk about today are methods which allow that for the first time in the last couple of years to be achieved. So I'm also aware that, of course, this seminar series is focused around earthquake physics. And so there's a question of why people who are more interested in that line of research should be interested in this problem. And so I just want to take a quick diversion to another project. And this is one that you have had a talk on in this seminar series. So you can look at the back catalogue and see a talk by Alexis Cartwright-Taylor quite recently. So I'm involved in this group of people who are trying to look at imaging rocks at a very different scale, so at the grain scale of rocks, and performing compression experiments where we compress them, and we track the differential stress across the sample and the increase in acoustic emission rates. And what you can see is as we just continue compressing, the acoustic emissions, so little fracturing events, happen at rates which are quite low, and then at some point they start to increase somewhat exponentially until, bang, the whole sample fails catastrophically along some plane. Now, what we've been trying to do in this group, particularly Alexis and Ian May and Ian Butler, Florian Frizais, for many years, have been trying to slow this process down. So we have a rig where we put our little sample in. It's only a centimeter across, 2.5 long, and we compress it in this rig while recording the acoustic emissions at 2 sensors, the 2 green sensors here and here. But what's important about this is in real time, we're recording the number of acoustic emissions per second, and that's shown by this blue curve as a function of time in seconds. And the rig is set up to dynamically respond to this rate. So once it reaches a certain point, we back off the compression pressure, the downwards pressure across the cell, and back it off such that we try to even out the acoustic emission rate. And what this means is that whereas before the stress would increase and increase and increase, and then bang, we would get this huge drop in stress, which would all take place in a very small period of time. Now we can extend the period of time over which that progression to failure occurs. And that allows us to take these blue dots, which are snapshots of the 3D structure of that sample there, by taking this whole rig to a synchrotron and taking samples, images every 3 minutes or so. So every 3 minutes, we can get a 3D image of that, and that allows us to create a 3D movie. So we just have a look at these movies. I don't want to take long on this because you've had a talk, but just to understand what you get from this. So here's that stress-strain curve. These are the snapshots, and in this movie, if I just look at the left plot first, you'll see that we're going to progress through those snapshots around the stress-strain curve, where this bit has been now very much extended over time. And now if you look at the right, you'll see what's happening to the rock as we compress it. So you can see the grains being compressed, and if in this ellipse, you start to see that catastrophic failure emerging. And if you look at this, we look at this in 3D, you can see now that this is simply the different components of strain, so shear strain, dilation, and compaction occurring. And let me just go back because this hasn't synchronized. Go forward. Right, there we are. So they're all playing together now. And you can see the emergence of the strain. And eventually, this plane, which is dipping away downwards towards the top, emerges as the catastrophic failure plane. But you can see, first of all, where my mouse is, you'll see a plane emerge here, an initial exploration of a different plane, then another, and then finally this one in which the failure takes place. So these experiments are fantastic. They show us what's going on. But there's one problem with them, is that they're only imaging kinematic properties of the medium. So they're telling us what happens, but not why it happens. And the reason I say that is that we can say at a macro scale why it happens. They happen because we're compressing the sample at the bulk scale. But why each particular little part of this rock fails is because of the stress and the mechanical strength at each particular point in the rock. And we don't know the stress at each point. So we don't know the stress-strain relations that are controlling these fractures, because we can only measure stress in the bulk sample, or we can model it on the interior, but then that depends on the models. So the dynamic properties at the grain scale are inaccessible in 3D currently, but here is where seismic inversion and monitoring of exactly the same kind as I just showed you for the large-scale Earth could help us, because at the very least, seismic inversion will get us elastic constants, which relate stress to strain. Now, it's a different frequency of deformation, of course, but nevertheless, which gets us some sort of dynamic properties. So wouldn't it be ideal if we could also do 3D seismic imaging of these samples at the same time and get dynamic properties? So that's another reason why hopefully people on this call would be interested if we could potentially have 3D or 4D monitoring of volumes of the Earth or of rocks in 3D and 4D. But to do that, we've got to get over this hurdle of being able to assess the uncertainty in full waveform inversion. So that's what we're going to focus on. Now, because we're talking about uncertainty, I'm going to be using Bayesian inference, and that is all based around Bayes' theorem, which is this formula on the screen. Now, the nice thing about Bayes' theorem is it gives us this quantity on the left, which we call the posterior probability distribution function, PDF. And this is the probability that any particular model of the Earth is true, given, that's the vertical line, any observed data that we have. So that's what we want. We want to know, given the observed data, which is fixed, that's what we've observed, what is the probability distribution over the set of models? That's our target. And Bayes' theorem says, well, this is given in terms of three terms. The first is called the likelihood, and this is the same, almost the same as the posterior, except the terms are reversed. So this is saying, well, if that particular model that we're considering right now is true, what is the probability that we would have observed the data that we measured? Now, the way that we would evaluate that is we would take that model, we would forward simulate the data that we would record if that model was true, and we'll compare that simulated data to the observed data. If they're very far apart, then it means it's quite unlikely we would have observed that data, and so the likelihood is low that we would have observed that data, and that means that this model is probably less likely to be true. Whereas if the simulated data matches the observed data very well, then the likelihood will be larger. So that's how we evaluate the likelihood, and it involves a forward model simulation there. So for each model, we have to simulate the data. So that's often the expensive part of our problem. So just bear that in mind. The second term is called the prior distribution. It doesn't depend on the data at all. So that's what we know about the model independently of the data, and specifically, from a Bayesian point of view, it has to be prior to considering the data. So ideally prior to collecting the data, or at least prior to looking at the data and being biased by the data. And the third term is called the evidence. This doesn't depend on the model at all, and so we're just going to treat that as a constant because it only depends on this observed data, which will be constant once we've observed it. So this is just a normalizing constant. So what we want to find is this posterior distribution. Now, if all of those terms on the right have closed form distributions. So what I mean by that is we have an equation which describes them. So for example, let's say they were all Gaussian distributions as a function of the model parameters M. So we have a Gaussian prior and a Gaussian likelihood. Then we could just take those two formulae, the two formulae for the Gaussian distributions, and multiply them together. And we now have a normalizing constant dividing these two distributions. In other words, we know exactly the equation of this posterior distribution. We have the result. The problem is that because we have a forward model in there relating the model parameters to the data in the likelihood, in fact, although our data observations might have Gaussian uncertainties, when those are translated back to the model in the likelihood term, they're going to be usually strongly non-Gaussian. In geophysics problems, there are few problems that are truly linear. And so if we use a non-linear relationship between these two, then we're going to warp that Gaussian into something else. And typically, because forward functions are not analytic, they are numerical, we will not know the closed form for this likelihood, and so we won't know it for the posterior. So it's not going to be as simple as that. Now, if we don't have closed forward distributions, then we have to evaluate this numerically, which means we've got to evaluate it for some model M, or some set of models M. And the question is, which models? Which ones are we going to choose? So one way that we typically explore the space of models and explore their probabilities given the data is to use methods, Monte Carlo methods, often Markov chains. The only issue with these in higher dimensional problems is that they become computationally expensive, and we'll talk about that a bit later. And so what this talk is about is when we get to 3D, 4D models, which are going to be very high dimensional, is there anything else that we can bring to bear in the problem? And in particular, I'm going to be discussing what are called variational methods, which are related to methods that have come out of the machine learning community. In fact, many of these variational methods have come out of the machine learning community. But they're not your standard neural network time methods, even though some of them use neural networks. So I'm going to be talking about these and seeing whether they bring anything useful to help us evaluate these in real-world 3D problems. So my agenda today, that's been a long introduction. I'm going to start with an example, which is going to be really a motivational example for using travel time tomography. I'm going to be using neural networks to perform the travel time tomography, and we'll see that it does, these methods do actually a pretty good job, but also they highlight an issue. And that's going to lead us on to discuss what's called the curse of dimensionality. And between them, these two first sections of the agenda will motivate why we need to bring in variational methods at all. So then I'll bring them in finally, two-thirds of the way through the talk, and we'll discuss how they work on full waveform inversion, this really hard problem. And then finally, after looking at them in 3D, we'll look at them in the monitoring case where we have time-dependent repeated surveys. So let's get started. So let's talk about travel time tomography using neural network inversions. And I'm going to be using a special kind of neural network here called an invertible neural network. So we're used to neural networks if we train them in supervised mode. Well, first of all, neural networks are simply very flexible functions. They're functions that can be tuned. So a linear graph, a linear function, just ax plus b, that is a function that can be tuned. I can change the a and the b to tilt the graph to fit data to get a best fit linear trend through any data set I like. And that data set will be an input, so an independent variable, say imagine on a horizontal axis, an output on a vertical axis, and we'll get a linear fit to those data. That is a very simple function. Neural networks are just much more complicated or complex functions made of very simple components, which allows them to be trained, or which is another word for fit, to the input and the output data. So they're functions that take an input, they give us an output. So we're going to have, let's imagine that we've got lots of input and output pairs, and the input here is going to be our models, our Earth models, and the output is going to be the data. And so the forward problem that we normally talk about in geophysical theory is going to take the model parameters and forward simulate the data that we have. And we could train a neural network to emulate the forward function. And we might do that, but a lot of people do that because the forward functions are often very expensive to simulate. And so if you can do a whole load of simulations up front and train a neural network to go to emulate that function, neural networks can typically be evaluated very, very rapidly. And so that then speeds up the use of forward functions when we need them. Now, invertible neural networks are a very special kind or formulation of neural networks, because while they are trained or learn the forward function, they also learn the inverse function. And they do that, and that's going to be obviously really useful to us because we want to then go out and measure some data, and we want to project it back to find what are the Earth models that are consistent with the data. So it's going to learn to evaluate our inverse problem. Now, just to introduce to show you how this works, the reason that they can learn both ways is due to the use of this special structure. It's called a coupling structure between the input and the output. And what was the input here is going to be a vector, usually, so there'll be an Earth models. So let's say it's a vector x, and we split it into two parts, so x1 and x2. And we want to map that Earth model in these two parts onto the data, which is going to be in two parts, y1 and y2. So the way invertible neural networks work is they pass this part of the data, x2, along this branch. It's going to pass right along here. But as it goes, it's also going to pass up this branch here. And as it goes up here, we're going to pass it through this function here, S2. As it goes up this branch, we'll pass it through another function, T2. And we're just going to get some outputs from those functions. And those functions can be anything. So we're just going to get some outputs from those functions. We're then going to element-wise multiply. So if you like, take a dot product between this vector and the output of that function, and we'll add it to the output of this function. And that's going to give us a new vector, y1. Y1 is then going to propagate right along to the end and go into the output. But it's also going to go down to almost kind of symmetric paths, and it will get passed through to other functions, s1 and t1, and then we'll do a similar operation, dot producting with x2, adding the result of t1 to get this y2. And then we simply concatenate these two, put them together to get our output. Now, this is very odd. It's very particular. It looks as though I've done something very unique and sort of particular here just to get something that's going to work. And that's exactly what has been done. The reason that we've chosen this special structure is that we can write down the relationship between the input and the output just in these two equations. So these two equations are going to show us. Now, in fact, what I didn't say is as these get passed through, they also take the exponential before we do the dot product. That's these two exponentials. But other than that, it's exactly as I said. So we take x1 and x2. x1 and x2 get passed through this to give us y1. y1 gets plugged in here, and that gives us y2. And so we see how we've managed to take our inputs, x1 and x2, to the outputs. Why we want these equations is that they can simply be rearranged into those equations, and these ones take the outputs, y1 and y2, and predict the inputs, x1 and x2. In other words, analytically, we can just rearrange these equations to give us the inverse solution. And what is really special about this arrangement is that S1, S2, T1, and T2, these functions in the middle, can be anything at all. In particular, they can be fully connected neural networks or convolutional neural networks, any kind of neural network you like, with an input and an output of the required dimensions. What's more, with this structure, the Jacobians, the derivatives of the input of the output respect to the input, are very cheap to evaluate. They're analytic from these formulas. So it's a very special structure, and it means that we can take usual neural networks, which simply go in one direction, that take an input and then give us an output, put four of them into a structure like this to form a composite neural network, which can work in both directions. So let's see how this works. So here is a tomography problem. So I've got a model on the left, which just consists of 11 by 11 cells. And these cells are just full of random seismic wave velocities. That's the colors shown on the scale here. Chosen from a prior distribution, which just says that they are uniformly distributed as far as we know. We know nothing else, and then that they lie between 0.5 and 2.5 kilometers per second. So this is a random model from that prior distribution. We've then got these triangles, which are here, the black triangles there, all the way around in a square. And they surround a 9 by 9 section of this model. And we're going to use travel times measured between all of the different pairs of these triangles. So these are receivers, and we imagine that we can get travel times between all of them. And that will be our data set. And we'd like to use those to do tomography of that 9 by 9 region in the interior. So for this model, for example, what we will do is we will forward model. So we'll use an iconal forward solver to calculate the travel times through this model. And these are the travel times over here on the right. And this is a travel time matrix between each receiver, say between receiver 5 and receiver 2. This is the travel time in dark green, so somewhere here, about 4 seconds, etc. You only show half the matrix because the travel time between receiver 5 and receiver 8 is the same as the travel time between receiver 8 and receiver 5. So we only need half the matrix. So what we're going to do is we're going to take 100,000 different random models on this side, And because the iconal solvers are very fast, for each one of those, we can simply simulate the corresponding data set. So we're going to have lots of pairs of models and data. And we're going to use that as a training set to train the invertible neural network. So in other words, we're training these 4 subnetworks in the middle to emulate functions such that we emulate both the forward function that takes a model and emulates the data, but also simultaneously the inverse problem function. Now, the forward function in this case is unique, but the inverse problem is definitely not, because we know that there'll be a family of models that are consistent with any particular data set if given that data has some uncertainties. So the way that we actually introduce the uncertainty, because their data set is going to be fixed when we measure it, and so every time we put the data set in, we would get the same velocity model in it. So during training, we combine the data set with a set of what are called latent variables shown down below. So these will just be latent variables chosen from a Gaussian distribution. And each training pair will be allocated one uniformly distributed value for a set of latent variables. And by doing this, we in fact train the neural network. For the inverse problem, we train it to output to take not just the measured travel time data, but also a value of all the latent variables. So a vector of travel times and a vector of latent variables will go into this side, and each time we put in a vector, we will get a vector on this side, which represents an Earth model. And by selecting randomly different values for the latent variables, we will get different models out on this side. And there's a trick which isn't displayed on the side, but it's really the trick that's embodied in the objective function that we use for training this network, for training those subnetworks, that ensures that as long as we have training pairs and latent variables, the distribution of models that we get out of this process will be the Bayesian posterior probability distribution. So in other words, we can simulate 1,000 of these models using the inverse model, and we can those 1,000 models will be distributed according to our uncertainty distribution. So it's a very particular choice of a network, a network structure shown here, and also the objective function used to train it that allows us to do this. So we do all that, and we can now look at the solution. So let's take a particular example. Here is a model that we'll call the true model. So this is actually still a 9x9 grid of random values. I've just interpolated it here so that it's easier to see the patterns with the eye. I'm just having a grid. And this is the corresponding set of travel times. And so we're going to take these travel times and we're going to put them into the trained neural network, and we will run the inverse problem 1,000 times with different latent variable values, get 1,000 different structures, and that's going to allow us to calculate at each point. We can calculate the mean velocity, standard deviation, we can calculate covariances between different points, and so on, whatever we would like to, whatever statistics we would like.
Andrew,
so yes.
It's Chris. Sorry to interrupt, but maybe other people have a similar question. I guess it's probably a dumb question for me, but when the latent variables here in this particular case, do we know something about them? Are they connected to uncertainties in either side of the phase velocity measurements or travel times?
No, they're not connected at all physically in any sense. And all we do, they're only there to create randomness in the inverse function. So what we do is we choose any distribution we like. There could be a uniform distribution, a Gaussian, a Poisson distribution, anything we like. But we allocate one set of values for all the latent variables. Say we had 10 of these, we would have a 10-dimensional latent space. And within that, we just simply assign for each training pair of input and outputs, if you like, we assign one random value to this. And it means that the reason we do this is that, of course, when we do the inverse problem, the data distribution is going to be fixed. But every time we rerun it, we can simply take a random distribution from this 10-dimensional Gaussian, and we're going to get a different output.
I see.
So they're unconnected. They're only there to give randomness. The information in the inverse problem is only provided by the training data, which consists of the input and the output, or the models and the data.
Got it. Thank you.
Okay. So here's our real data for our real structure. So let's now invert that using the trained invertible neural network. And this is what we get. So the INN, the invertible neural network, gives us this model. And what you can see is it's pretty good. It's not perfect, but it's got the blue. You can see the blue patterns are in all the right places if you compare the two models. The red is in roughly the right places. And so it does a pretty good job. And after using this trained network, we get this mean structure. So this isn't a model, it's a mean over 1,000 models in just 2 seconds. Now, the alternative will be that we could take that data set and invert it with, say, a Markov chain. And we just did this with a very simple Markov chain, Markov chain Monte Carlo, and we get this structure. And this took us, on the same processes, this took us 3 days. Now, the solution perhaps is slightly better in this case. You can see perhaps a slightly better structure than this one. But of course, that came at a cost of the extra computation. So what we can see is that the invertible neural networks give us a reasonable estimate of the solution very quickly post-training. Now, we don't just get the mean structure. We can also look at the uncertainties. And so we can take all of the different 1,000 realizations of the model, and we can just calculate the correlations between the different cells in the model. And that's what's shown in these two matrices. So on the left, we have the correlation matrix from the invertible neural network, on the right from the Markov chain. And you can see they're not identical, but the network in 2 seconds is getting something out which looks pretty similar in overall structure to the Markov chain. We're seeing these 3 diagonals. We're seeing the cells that are just off diagonal. We can see they're red, which indicates there's a negative correlation between each cell and its neighbor. The next diagonal is the correlation between each cell and the cell below, and that's also red. So that's telling us that neighboring cells are trading off. Whereas 2 cells below, in fact, the correlation is positive because it's blue. We're seeing that in both structures. But again, the invertible neural network is getting that very, very quickly post-training. So just a summary of this motivational example. We can see that these networks can solve small Bayesian inverse problems, here with 81 parameters, 81 dimensional, very quickly post-training. And what's more, the training time for that network was about 3 days, which is about the same as 1 Monte Carlo run. So in other words, in the same compute time, we would have been able to run 1 Monte Carlo run, or we were able to run 1 Monte Carlo run and train 1 invertible neural network. So, and the invertible neural network has the advantage that it can solve any inverse problem, or estimate. Give us an estimate of the solution to any inverse problem, whereas Monte Carlo is simply solving that 1 inverse problem with that 1 data set. Now, what this means is that training of the network, all the work we did up front to train it over that full prior distribution is a strength, that's for sure, because now we can solve lots of different inverse problems just very rapidly, just in 2 seconds of computation. But it's also a weakness. Now, why do I say that? Well, if we look back at this plot, while we've got the overall structure correct, the actual values are deviating somewhat. So, for example, if we look at this particular little square here, we can see that that indeed appears on both, and it's roughly equivalent. But if we look down here, for example, we're not really seeing that at the same location over here on the left from the invertible neural network. So it's getting us, as I said, an estimate of the solution, but it's not getting us the same one as the Monte Carlo. Now, remember that the Monte Carlo has focused on it's focused all that computation on just getting this one solution, whereas the same amount of computation, roughly, has been focused by the network on finding all solutions to all problems. So we would expect the solution to this problem probably to be better from the Monte Carlo method. So therefore, we would hypothesize at least that this solution is less accurate than that one and is a little bit different. So therefore, this training on the initial distribution is also a weakness. It's a strength because we can solve many problems. It's a weakness because we don't get the exact or the accuracy that we get if we focus all our effort on that one solution. Now, the question is why? Why is this happening, and how bad an approximation can this get? And for that, we have to consider the curse of dimensionality. So now let's just have a look at something, at neural networks in general. So when you learn about neural networks for the first time, you typically get slides that look like this. And you're taught that neural networks work a bit like regressors. So we have an input variable, let's say the model parameters here on the horizontal axis, and we have some data on all the vertical axes here. And we have lots of little samples, little points here. They're the same in all the plots. And we are going to train a function to emulate the relationship between the model parameters and the data. So here's what I described earlier, using a linear function to emulate it. Over on the right, we have a log linear. Here we've got a categorized variable for the model parameters, where we split it into specific regions which have the same value. And over here, we've got a generalized neural neural network type model, which is used to fit the data. And clearly, here, these neural networks are acting as regressors. They are regressing through the data to find out the best fit compromise to the relationship between M and D. Now, that's fine, but these graphs are almost always shown with one model dimension and one data dimension, because that's what you can display on a page. So let's have a look at what happens when we have two model dimensions. The number of parameters is 2. So we've got M1 and M2. And so any particular model is going to be a point on this plane. And if we want to, so the points that we're going to be regressing through are going to be models given by a point on the 2D plane, and then simulated data for that point, for that model. So to actually generate data that we are going to regress through, we have to explore this plane. So we could take, say, 10 samples per model parameter axis, something like that, make a grid of different models, different values of M1 and M2. And for each of these points, then we can evaluate the forward function, which emulates the data. And that's going to give us 10 by 10, so 100 model data pairs, which we can then use to train the network to emulate the relationships between model and data. The problem here is that this is in 2 parameters, in 2 dimensions. Here we have already 100 samples, and clearly if we have 3, we'll have 1,000 samples, and by the time we get to 20, we have 10 to the power 20, it's utterly intractable. So what are we to do? Well, I arbitrarily chose 10 samples per dimension. So let's imagine that we just cut this way down and just go for 2 samples per model parameter axis. So we now, in 2D, we have 4 samples, 4 model samples, which we're going to emulate. Now, clearly that's much better. When we have 3 dimensions, we'll have 8, 4 dimensions, we'll have 16. But in our tomography problem, we had 81 dimensions. And if you just carry on down that sequence, you end up already with just 81 parameters, with 2 followed by 24 zeros. That is the number of different model samples you end up with, just to explore that 81-dimensional space. Again, way beyond what we can do. So what can we do? So in the example that I showed you before, we used 100,000 samples and the travel time to train the network. So 100,000 samples to explore the parameter space. So what if we did better than that? Say we could do 100 times better than that. We used 1 million samples and distributed them throughout this 81-dimensional space. Well, if we imagine that, if I just go back to this case, so what we've done here is we've said, well, if we take 2 samples per dimension, we end up with this huge number of samples. And that's with 81 dimensions. So in other words, if I take the 81th root of this number, I'm going to get 2. And that's going to be the average number or expected number of samples per dimension, or the effective number of samples per dimension, let's say. So it's going to be almost exactly 2 in this case. So we can play the same game with our 10 million samples and say, well, let's take the 81th root and work out, well, how many samples per dimension is that? It's 1.2 samples per dimension. In other words, in this 2D space of M1 and M2, we would expect 1 training example. Now, that's really problematic. I cannot regress through 1 sample. Now, what else can we do? Well, we could, as I said before, use neural networks to speed up the forward function. So let's say we could speed up the forward function by a factor of 1 million. It's not unheard of to be able to do that. That's within the bounds of possibility. And so in that case, perhaps, if the forward function is a limiting factor, instead of getting 10 million samples, I might be able to get 10 trillion samples in this 81D space. So if I now take the 81st root of this number, what's the effective number of parameters, samples per parameter? And it's 1.4. So in this 2D space, I expect to have 2 samples. And this really is way beyond the largest number of samples I have seen used in any geophysical problem already. And so with that extra large number of samples, we're still only getting 2 samples. So what this means is that neural networks are not regressors at all. The intuition that we get from looking at simple 1D spaces does not extend to our higher D spaces. They're not regressors, they're extrapolators. Because these samples selected from the prior distribution that we use to train the networks are going to be nowhere near the true Earth sample. If we only take 2 samples in a space, the chance of the true Earth sample being anywhere near it is very small. So this means that the neural networks are extrapolators, and that explains why they don't give exactly accurate results, or very accurate results, even in only 81 dimensions. What we also learned from this little thought experiment is that the speed of the forward problem is essentially irrelevant. In this case, when I took the best possible speed up 1 million times, we went from 1 sample per 2D space to 2. It doesn't solve the problem. So speeding up the forward problem is not going to help us solve these inverse problems. We use it by what we call prior sampling. So sampling the space according to the prior and training the networks to regress through those samples. If, for example, we wanted to increase the number of samples for this 2D space to 3, we would have to have a speed up of 10 to the power 10. And maybe in the future that's possible, but it's still not going to solve this, our training problem. So prior sampling is usually going to be impossible for these high D spaces, particularly because this is only 81 dimensions. If you had a gridded image like the one you saw there on your camera, you would take the camera back. It's barely a photon. So 81 parameters is nothing. And still we can't sample space. So this means that instead of sampling the prior and doing all the effort up front of training the neural network so that we can then solve inverse problems fast, we're going to have to do something else. And that something is normally the most efficient thing we can do is to actually explore the posterior distribution instead of the prior. Now, the reason that that's a better or an easier problem to solve is that as long as the data is very informative, what that means is that we're going to take the prior space of possible models, and it's going to be shrunk down hugely by that informative data. So we're left with a much smaller subspace of that parameter space, which gives us the possible models, the models that are consistent with data. In other words, the uncertainty is shrunk. And so we only have to explore that part of parameter space with whatever number of samples we've got. So that's what I'm going to do for the rest of the talk. This has been motivating why I'm not simply training neural networks to do this. We're going to have to use some more sophisticated machinery to explore the posterior distributions. And this is where we come to variational inference methods. Variational inference works in a different way. So it replaces stochastic or random sampling that's used in Monte Carlo methods with optimization. And optimization algorithms are really quite well understood, so that we can bring quite a lot of intuition to optimization algorithms that are much more difficult with random sampling algorithms. And in variational methods, we use optimization to optimize probability distribution functions. So what does that mean? Well, they start typically by defining a family of distribution functions. So this could be the family of all Gaussian distributions, for example, or all distributions that we can make by summing two Gaussians together, or n Gaussians together. So some family that we define, and we'll call that family capital Q. And within that family, we're going to try to solve an optimization problem. Now, this equation here might look unfamiliar in notation, but it simply describes an optimization, and I'll show you what it means. So in this notation, P is going to be the posterior distribution that we're trying to estimate. We don't know it up front, it's unknown. That's what we would like to find. Q is going to be one of the distributions in this family that we defined already, Q. So this family here is called the variational family of all the PDFs that we're going to consider. And this KL here is called the Kullback-Leibler divergence. It represents a measure of difference between the distribution Q and the unknown posterior, in our case unknown, posterior distribution P. And we can estimate that by sampling, by taking a small number of samples of P and of Q. Now the KL divergence is a really useful metric because it's always positive and non-zero except if Q equals P. So in other words, by minimizing the KL divergence with respect to Q, we're going to find the Q which is closest to the unknown distribution. And all this in notation means is take the argument Q, in other words, take the value of Q, which minimizes the KL divergence between Q and P, in other words, minimizes the difference between them. And that argument, the best Q, we'll call Q star. Now, clearly that minimization, that's an optimization. Okay, that is, we're finding an optimal approximation to P within Q, within this overall family, and we've clearly then changed from stochastic sampling to optimization. Now, what's more, it turns out that if we make different choices for this family capital Q, this leads to different algorithms. So let's just have a look at one in a schematic case just now. Actually, it's a real numerical worked example. So in this case, the blue curve is the unknown posterior that we're trying to approximate. Q here, the red curve, is just an initial estimate of that. And in this case, it's starting at a Gaussian. And we're going to investigate the family of probability distributions that can be obtained by perturbing this Gaussian distribution in certain simple ways. And so we're going to iteratively perturb it to minimize the difference between these two distributions. And so if we iterate, in this case, 1,000 times with very small steps, we see the red distribution being perturbed, another 9,000 steps, and it's getting pretty close. And if we do another 10,000 steps, we see it hasn't changed very much. So this optimization has reached its, roughly speaking, its best point, its optimum point. And that red distribution is now our estimate of the posterior. So that is our Q star. So that's how these optimization problems work. They're fitting the shape of the distribution. Now, the way different algorithms emerge is, for example, one variational method just finds the best fit Gaussian. So we don't actually have to iterate through this process. We simply find the Gaussian that best fits the background distribution. So we're going to perhaps adjust the mean and the variance in this case until it spans in an optimal way the difference, reduces maximum the difference between the two. And that method, roughly speaking, there's a little transform that's included in it, is called ADVI, which is automatic differentiation variational inference. Because that's a mouthful, we just call it ADVI. Another way is that we could use neural networks to warp this distribution Q. So we could have neural networks being trained just to warp the distribution in each iteration, moving around here. And that's what's done in a family of methods called normalizing flows. Alternatively, we could use neural networks to predict Gaussian mixtures in what are called, for example, boosting methods. Or we can still use samples. So remember, in Monte Carlo, we use samples. We sample this blue distribution. And gradually, by taking more and more samples, we see the sample densities and what emerged to peak here and here. We can use samples in variational methods as well. Here's an example. So here is an unknown 2D posterior distribution in blue. And our parameterization of the probability distribution is just going to be given by the density of a set of samples. And here we've got about 80 samples here, the dots, and their density is going to represent the probability distribution. So clearly it's denser here. Actually, these are selected from an initial distribution, which is a 2D Gaussian, similar to the previous case, the 1D case. So we start with a 2D Gaussian distribution. And what this algorithm does, and this algorithm is called Stein variational gradient descent, another mouthful, so we just say svgd. This algorithm is going to gradually perturb the particles until they best distribute across this blue distribution. Now, the way that this algorithm works is, again, this looks a little bit complicated. I'm just going to take you through it, and it's not so complicated. So we start with a set of models, samples, which in this algorithm are going to be called particles because they're going to move. We're going to perturb their position in parameter space iteratively until they approximate the posterior distribution. So we start with a set of models, which we call particles, and at iteration j+1, we're going to move from their position at iteration j to a new set of positions by just making a small perturbation in direction phi star. And this phi star here is actually given by this long expression here. Now, this looks complicated, but in fact, these terms are really not that complicated. So, for example, this term here are the standard Jacobian or gradients that we would use in any inverse problem, any linearized inverse problem. We would have a Jacobian matrix, and that Jacobian can be used to construct this matrix of gradients of the log of the probability distribution. The other terms here and this first one here just involve this k over here on the left and gradient of k over here. And k is just given by this simple function down here. It's just a distance measure of the distance between pairs of models. And clearly that is related to their density. So that's the connection between the models of particles and the probability densities, those. But it's very simple to evaluate. It's just the difference between them. Euclidean norm exponentiated. And so we can easily evaluate these terms, and at each iteration, that gives us the direction in which we should move the particles. How does this look? Well, here's the same example. There's their starting point, and these are the iterations as those particles move through various iterations, moving in that direction, phi star. And you can see that they interact. They're not moving one at a time. They're moving all together to self-distribute such that their density represents that distribution. So this is still giving us samples, just like a Monte Carlo example. But what is completely different from Monte Carlo is that this is an optimization problem that gives us this final set of optimally distributed samples. Now, there is a problem with this algorithm. Basically, the number of samples you end up with is the sample number that you start with. And so you have to start with a large number of particles. And that, because we can't cope with too large a number when we're going to iterate through their positions, this is going to lead again to undersampling in high-dimensional spaces. So, and you can see that if we just look at another example. Here's a simple 2D Gaussian we're trying to fit with 20 samples. Now remember, in the prior sampling case, we expect about, well, fewer than 2 samples per dimension, typically. But let's say we had 20, sorry, in this 2-dimensional space. So let's say we had 20. You can still see that even when they get optimized now, that they're really not sufficient to approximate the density of the Gaussian. You see clusters here, a cluster there just by chance occurring, and really it's not ideal. So there is another version of SVGD, which is called stochastic SVGD, where we add a specific noise term to the iteration at each point. And it's chosen such that you can keep, at each iteration, you keep the samples. And so you build up samples during each iteration. And this gives you many, many more samples by the end of all of the perturbations. And it does gives you far denser sampling for your posterior. So this is going to be called small s, stochastic SVGD, whereas the previous one was just SVGD. So these are the algorithms, well, some of the algorithms. They work in a very different way. So let's just see them now at last applied to our problem. So here's an imaging problem. This is going to be an Earth model. We're going to simulate seismic sources and receivers. We will emulate the waveforms of waves propagating through these models, and the waves will refract and reflect and come back to the surface, and we'll record a set of seismic waveforms at all the different, one at each receiver for each source. And so we're going to get lots of waveform data. This is going to be our data set. We're going to invert all of those waveform data for the family of models that are consistent with those waveforms. That's what we want to do, and that family is going to be described by our posterior distribution. Now, we're not going to do this in 2D just now. We're going to jump straight to the 3D problem, because that's where we need to be able to apply this. And this is the real advance that we've made in the last year or so here in Edinburgh, is to be able to scale these methods. Because they're optimizations, we're able to scale them to 3D problems. So here's a 3D problem. This is a 3D synthetic model. It's going to represent the true Earth structure. And our data set is going to consist of 10,000 receivers. So these little, what might be a green haze to you is actually 100 by 100 green dots. Those are the receivers. And then we also have these 81, so 9 by 9 grid of red dots here on the surface. So 81 sources. So we're going to get a lot of different waveforms, one from each, at each receiver from each source. And we'll record them in the frequency band 2 to 10 hertz. We'll then add 2% noise to them, just random noise, and that will be our data set. Now, the model parameter, the model that we're going to invert for, is the one in front of you. You can see it's coarsely parameterized. If you zoom in, you can see there's little cells here. But even this model, this coarse parameterization, has already 650,000 dimensional space. It's 650,000 parameters. So there is no hope of prior sampling in this space. So the question is, how about these optimized posterior samples that we've been looking at? Now we're going to use a prior distribution shown on the right. So a prior is simply going to be a uniform distribution over here. And we're going to solve the problem, and I'm going to show you solutions on a vertical cross-section below this pink line here. So we'll just look at 2D cross-section. Because this model is fairly homogeneous, not entirely, but fairly in the distance, the dimension away from us, we expect to see structures a bit like the ones in the front here. Now, the nice thing about these fully nonlinear methods is that we can solve them with no additional regularization. Now, that is not the case for standard linearized waveform inversion methods. You have to add regularization to make the problem overdetermined, otherwise you get no solution. But here, the only regularization, if we call it that, is provided by this prior distribution. And so it just says the parameters lie within these bounds as a function of depth, the p-velocity. So we're really seeing here what information about the model is in the data alone without additional arbitrary, usually, prior information. So let's have a look at the solution. So we're going to look at the family of solutions that are possible given all of that waveform data. And here is an example model. Now you can see those curved interfaces that we expect to see. You can see that there's structure that makes sense up at the top, but as you go down to the bottom, it gets very noisy. And remember, we're not just going to find one model using these algorithms, we're going to find many. And so I'm now just going to step through all of the samples that were found, or a number of the samples that were found using one of these sample-based SVGD algorithms. Now, these may not look very good to you.
Andrew.
Yeah.
Now, finish this slide, but given the time, I wonder if we want to make sure that people don't have questions at this point, especially people who wouldn't be able to stay with us. Would you like to just have a quick pause and make some check?
Absolutely. Yes. Sorry, I didn't realize the time.
No, don't worry, it's fine. I think we still have plenty of time. But yeah, how about a call for, let's call it intermediate questions at this point? Does somebody have something that they'd like to inject right now? Or, okay, then, because I should have questions, but I'm certainly happy to wait until the end.
Yeah, I had a question. That's Vladimir Kazay. Sorry for jumping in. I was wondering about the hyperparameters. How do you select H and epsilons for the inversion? In the SVGD and in stochastic SVGD, you have even more, right?
Yeah. So they are usually found just using. So there are some rules of thumb for H. I should say that it's not without problems selecting those parameters. There are only 2 of those parameters, but there are rules of thumb to find them. So we select H using an average distance metric between the samples, and we find an average. I've got an exact formula right now, but it's in the papers that were cited there. And the epsilon, which is just the distance that we perturb it, that was just simply chosen to be large enough that, or small enough that we didn't, that we could still get through enough iterations to converge, if you like. So they were quite pragmatically chosen, those. And it isn't without issues. And I'm going to show you in a moment that, in fact, that SVGD solution has issues. So it isn't perfect. And it is something to do with probably partly to do with those parameters, but really it's to do with the fact that we have so few samples in such high D spaces. So there is a bigger problem, which is the undersampling problem with SVGD. I'll show you that in a minute.
Maybe, yeah, Andrew, go ahead. But if somebody else has a question they'd like to ask right now who can't stay with us, then please go ahead. Okay, Andrew, yeah,
Yeah, I'm really sorry. So I hadn't realized I've
Perfect,
been going slower than I thought.
Yeah, it's always hard to keep track. Don't worry, keep going. Fine.
I'll shoot through these because these are just examples. So what we can do is each of these is a velocity model. So we can take each velocity model and use it to back project the data. In other words, to migrate the data back inside into the subsurface and construct an image. So migration is a standard practice in industrial imaging. And I'm not going to go into it, but essentially we just project the data backwards through the velocity model into the subsurface. And for each of those models, we're going to get a different migrated image, and here they all are. And so now you can see that how the uncertainty propagates into actual image uncertainty. So for example, let's say this was our reservoir down here. We would be able to look at this set of images, and if you look right here where the mouse is, sometimes that structure is open, and sometimes, most of the time, it is closed. So that would give us a probability of that structure being open or closed, which would allow us to make a risk-based decision, for example, about whether to use this as a storage reservoir. Is it looking closed if this is our seal up here? So that kind of interpretation, that kind of uncertainty then becomes interpretable. Now, the other thing about these models is they're incredibly speckly. Now, that's because there's nothing in seismic waveforms that says that the models should be smooth. Nothing at all. So if you see a smooth model coming out of full waveform inversion, it's only because the geophysicist has put it in there through the regularization. It is artificially constructed by that geophysicist. So that's what I mean about arbitrary prior information. The true Earth may well not be smooth. And if you inject that information, then the model family you get will be wrong. So that's why we're interested in these methods, because they don't require us to put in that extra regularization. Now let's just have a look at these models along 4 vertical profiles. And now we're just going to look at all the different velocities that we're getting in these models, and we'll just histogram them up. So now on each profile as a function of depth, we see in colors in the yellows, greens, and blues, we see the histogram of velocity values as a function of depth down here in the 4 profiles. The white are just the prior bounds on the velocities, and the red is the true value of the velocity curve. And what you can see is at the top, the uncertainty structure seems to do a pretty good job of spanning the true model. But when we get down the bottom, it does a pretty poor job. And this is because the uncertainties here are clearly too narrow. So the svgd algorithm, which was used to sample this space, is not giving the right uncertainty structure. And this is certainly, or almost certainly, because the number of samples here was of the order of 1,000, and we simply cannot sample a 650,000 dimensional space with 1,000 samples. It's as simple as that. So then we move to stochastic svgd, and this is the result we get. Now it's much more, again, speckly, but you see that the true model is indeed typically within the uncertainty bounds. Now, while the uncertainties are broader here, you see that where we do have very good constraints, they overlap now with the true model. And again, up in the top parts of the model where we've got very good information, we're getting pretty good constraints. It's not perfect. There are places over here where we don't encompass the true model, but this is a sample-based algorithm in the end, and we have a limited number of samples. And then we have what we call the Bayesian's dilemma, which is, well, this one looks like it does a pretty good job in most of the cross sections, but is it correct? We know the true model, but we don't know what the true posterior distribution should look like. And so the only way to assess whether it's a reasonable estimate of the posterior is to try it with a different algorithm. So we just constructed a different algorithm, which I'm not going to go into, another acronym, PSVI, and that one gives similar, roughly, results to the stochastic svgd, which gives us more confidence. And just to finish this section, I can see there's something appeared in the chat, so I'll stop in just a moment. I think we just have to ask why. are these two independent algorithms giving similar answers. We have a huge dimensional space and nowhere near enough samples to sample that space. Yet, somehow, we're getting some sort of handle on the uncertainties that looks reasonable. It's unclear. Maybe the data are really very informative. It's possible. We've got a lot of waveforms here. And so actually the part of the posterior space that's spanned by positive probabilities is very small. That's possible. It could be the problem is surprisingly regular. You know, waveform inversion we assume is very nonlinear. Maybe it's not as bad as we think, and we've got lots of data. Or perhaps both of these methods are wrong in the same way. And we don't know the answer to that. The only way is to try a third method and a fourth, and gradually we will work out the truth of this. And maybe I'll just, is there another question in the chat? I can't see it.
No, it was only.
Okay, that's fine. So then the last thing on this 3D models is just about the computational cost of all this. So these are the methods that I've mentioned. So there was the ADVI method that took 4,000 forward evaluations of the waveforms. And that's the expensive part, is the number of evaluations. The physically structured one that I didn't explain, but I alluded to, takes 6,000, and that's because these are actually quite closely related. SVGD, 400,000, stochastic SVGD, 80,000. Now, two of those, the SVGD and the ADVI, in fact, well, we saw SVGD did not give a very good answer, and ADVI gives a very similar answer to SVGD. So those ones are no good. The two algorithms that gave a reasonable or similar answer are the physically structured and the stochastic SVGD. And these, so the smaller of these is requiring of the order of 1,000 for evaluations. Now, it takes of the order of 100 evaluations for standard linearized 3D FWI. So it gives you one model, it includes arbitrary regularization and doesn't give you the correct estimate, any correct estimate of uncertainty. So in fact, that 6,000 at the top there is just an order of 10 more to estimate the fully non-linearized uncertainties in this huge space. So if it turns out that these are robust estimates, we find a third method that gives similar results, then, and we can do this in FWI, well, that's the biggest problem we have in seismic. So that means all of these other types of methods, travel time tomography, surface wave dispersion, inversion, and so on, these will all be tackleable in 3D using these variational methods. That's the end of my section on 3D. I could stop there, Chris, because the next section is just a set of examples on 4D. And I could skip to the conclusions. Maybe that's the best thing to do, I think. Is that okay with you?
Yes, I think that's probably a good idea. Give us a chance to have some questions and discussion before we wrap.
So I'll just show, so I'll start at I've just got 3 slides, I think, to terminate. So the conclusions overall are that we found that the prior sampling using a neural network, it fails in these nonlinear, very high D problems. And the speed of the forward model can't alter that conclusion. We simply have to explore the posterior distributions in these high D problems, not the problem. The variational FWI, the variational methods we just saw, they seem to provide these Bayesian uncertainty estimates that are reasonable for 3D properties. What I didn't mention is that when we moved from SVGD to stochastic SVGD, actually we moved from an optimization back to a Markov chain. Even though if I'd shown you the formula for SVGD and stochastic SVGD, they're almost identical, except the stochastic one has a little noise term put on the end. So they're almost identical, but one is an optimization and one is a Monte Carlo method. And this suggests that there actually are a whole spectrum of methods that lie between Monte Carlo and variational methods, just waiting to be explored, I think. What I was going to show you is that in time-lapse uncertainty, we get reasonable estimates of uncertainty on the changes in the structure over time. And what we showed in those examples, or I would have showed in those examples, is that if we estimate these uncertainties in this way, it's far more robust. in standard currently used double difference FWI methods to things like changes in the acquisition geometry between different surveys. If you estimate the uncertainties, you get robustness. And then I just had a couple of tasters of other results. In fact, using these variational methods, you can change the prior information at almost zero cost. So this allows you to change different geological conceptual models or regularization very, very quickly. You can, if you combine this with generative neural network models, you can test geological conceptual models. So is the model conforming to a set of fluvial channels, or is it a shallow marine sort of parasequences? You can test that quite quickly using these methods. It allows us to use geological information to regularize the 3D inversions directly. Again, because this is an optimization or an optimization-based Monte Carlo. And finally, there's a whole class of experimental design methods to optimize the acquisition design to maximize the information. And so with that, I'll apologize again for going over time. And these are just a set of, in dark are the papers that I've referred to in this talk. Obviously, a few are on, a couple are on time lapse, the 4D ones. And if you are interested in just learning about these methods, a good one to start with is this one in blue that I've put in the middle. That one gives a nice introduction to the methods. Thanks.
Beautiful. Thank you very much, Andrew, for a fabulous talk and a lot of interesting things, including this ending with wrapping things up and giving us some pointers. So yeah, please unmute if you'd like to join me in thanking Andrew. Otherwise, go ahead and turn your mic on and ask a question. There at the bottom of your screen, I'm sure you're familiar, we have this raise hand feature that looks like that, and it will put us in some order, but I'm not going to raise my hand just now. I'm going to invite other people to do that. And Andrew, if you want to continue sharing certain ones of your slides to answer questions, you're welcome to do that. But thank you very much, Andrew. So please open it up for questions. So someone raising there, yeah, go ahead. Ali.
Can I?
Oh yes, go ahead.
Can I ask a question? Or?
Okay, go back first, and then we'll go to Ali. Wait, Haj, sorry. Yeah.
Should I start or?
Please go ahead. Yes, do.
Okay, thanks, Andrew, for a wonderful, very interesting talk. I wonder, I mean, you start with the uniform variation or uniform variance, and during the iteration, do you update the variance, or you know, like I think we used to do with simulated annealing, or where you know the system learn about the statistic or of the prior in the evidence?
Yeah, no, we keep all of the distributions constant because the idea is that, you know, the prior information is what it is, so that doesn't change. The uncertainties on the data are what they are, they don't change. And so the solution doesn't change during these algorithms. All these algorithms are doing are exploring the solution space. Now, you mentioned things like simulated annealing, genetic algorithm. These are all optimizers. So we could use those algorithms not to characterize the uncertainty distribution, but to optimize the functions towards those distributions. That would be possible. And in fact, we have used genetic algorithms, for example, to do that. But those algorithms are not